Okay, now let's take one example over here. A simple tensile bar is subjected to the constant tensile force of F. Design the bar with the objective of minimizing the material cost under the factor of safety NF. The following is the limitation specified the design. What are the limitation? L minimum less than equal to L, which is less than equal to L max. So basically what we are going to do, we are going to select the material from the list of materials available. Okay, now purpose is to minimize the cost. Okay, so this is what the diagram, that is this is the cross sectional area A of the bar, and this is what the total length, and the force is acting at the both end. Okay, now what is the terminology? CM is the material cost of tensile bar, which is in rupees. C be the cost per unit mass of the material. Rho be the mass density of the bar, which is expressed in term of the kg per mm cube. Okay, A be the cross sectional area of the bar. NF is the factor of safety. Rho T is the tensile stress induced in the bar, which is Newton per mm square, and SY be the yield strength of the bar material. Okay, Newton per mm, which is expressed in terms of the Newton per mm square. Okay. Now the first we are going to design the primary design equation. Now the primary design equation, the most significant undesirable effect to be minimized. Okay, now what is the most significant undesirable effect to be minimized? And we are knowing about the weight and the cost. Okay, now right now here we are going to eliminate the cost of the material, or the cost of the part. Okay, so that's why the CM, what is the CM? CM is the material cost of the tensile bar. Okay, that is a total cost, that is the material cost rupees that we are going to minimize. Okay, so that's why the CM is equal to cost per unit of the bar multiplied by the mass of the bar. Okay, cost per unit of the bar multiplied by the mass of the bar, that is the total mass available multiplied by the cost per unit of the bar. Okay, that is C cost per unit multiplied by the mass of the bar, that is rho into the volume. Okay, rho into the volume. Now what is the volume? Volume is equal to A into L. Volume is equal to A into L, so that's why it will become C rho AL. Okay, C rho AL, where C be the cost per unit of the bar, Now we are moving over here to find out a subsidiary design equation. Here we are going to find out a subsidiary design equation. The tensile stress induced in the bar, which is given by that is rho T is equal to force upon area, that is F upon the area. Okay. Now why is a subsidiary design equation? Because we know the stress is equal to force upon area. Stress induced is equal to force upon the area, where F we are going to equate, or we are going to find out for the maximum value of the force. Okay, that is the maximum force you can apply divided by the cross sectional area available, which is present right over here, that is the cross sectional area. Okay, and that will become the forces acting at the both end. Okay, now rho T is equal to force upon area. Now this is the one more equation. Okay, but this is what the subsidiary or supplementary equation, and that we are going to use in the primary design equation. Okay, that's why it is separately written as a SDE, subsidiary design equation, that is stress is equal to force upon area. Now next, moving as per the sequence, that is the Johnson method of optimum design. The third one is the limit equation. Okay, limit equation, and already we know that is a sigma T, rho T is equal to what? SY upon NF, where SY is nothing but the yield strength of the material divided by the NF, factor of safety. Rho T is less than equal to SY divided by factor of safety, and in our problem they have given that is L minimum less than equal to L less than equal to L max, where the L minimum and L max is the maximum and minimum values of the length of the bar that we can take. Okay, so L minimum may be the 10 and L max may be the 100. Okay, so that is the length of the bar should vary within the 10 to 20 or 20 to 30 in this way. So that's why this limit is specified in our problem. Okay, so that's why we have taken, and these two equations gives the limit, that is this equation gives the limit to sigma t, and this equation give limit to the maximum length or minimum length of the bar. So this is called as a limit equation. Two limits equation in this. Okay. Now here we are going to sort all these parameters. Okay, we are going to sort all these parameters. Okay, now this is the first row. You will see the functional requirement parameter, undesirable effect parameter, geometrical parameter, and this is what the material parameter. I have to repeat again: the functional requirement parameter, undesirable effect parameter, geometrical parameter, and the material parameter. Okay, now they are written over here, and the columns specific, limited, and unspecific and unlimited, that already we have seen in our previous video. What is the specific, limited, unspecific, and unlimited parameters? Okay, now f and nf belongs to functional requirement parameters, and these are the specific values. F will have the specific value. Suppose f is the 1000 Newton, nf is 3, or nf is the 2. That is the specific value is given for that. Okay. Similarly, undesirable effect parameter, these are the sigma t and the cm. Okay, that is sigma t value is undesirable. Okay, that is this will have between, or it should be the lesser than the SUT value. Okay, sigma t, and where cm is the cost of material, and that is what we are going to minimize. So that's why it is the undesirable effect parameter. But this is going to be vary. Okay, because this is going to vary as the material changes. Okay, so that's why this will comes under unspecific and unlimited parameter, cm. Okay, now the cm sigma t, already we have seen over here, the sigma t is going to come, or it is lesser than or equal to sy and nf. So that's why this will comes under the limited. That's why it will come under the limited. Okay, now the length and area. Now length also it is in the limited, because we have written it in the L minimum, L and L max. Okay, so this is what the gives the range. So this will comes under the limited. And A also going to be vary, because the material is going to be changed. Okay, now how much A is there, that is not decided yet. Okay, similarly in the material parameter, these are not going to be changed, because this is for the specific material and it is going to be vary. So this will come under the again limited, C rho and SY. As material changes, this value also going to be changed, but this is going to change within the limits. Okay, now the combining the substitute equation and primary design equation, what we are going to get, Cm is equal to C rho F L divided by sigma t. Now how we are going to get? We are going to combine the SDE and PD. Now what is the PDE? C rho A into L. C rho A into L. Multiply by what? Or I can say here A we are going to replace with the F upon sigma t. Here you can see this is what the substitute design equation. Sigma t is equal to F upon A, and this A we are going to replace over here in PDE. Okay, now we will get the Cm is equal to, so this is what Cm is equal to C rho F L divided by sigma t. C rho F L divided by sigma t. Okay, now by combining limit equation in the PDE, okay, already we have combined SDE with PDE. Now we are going to combine the limit. Okay, now there are the two limits, that is the Cm is inversely proportional to sigma t, and one more is limit specified for the length, that is Cm is directly proportional to length. As because length increases, the cost of the material is also going to be increases. Okay, now by combining this we will get Cm is equal to C rho F upon Sy upon Nf multiplied by the L minimum, that is the length. We are going to choose always the lesser one. Okay, because otherwise the cost will also going to be increased. Okay, because here you can see directly proportional, so we are going to choose a minimum length. Okay, and this Sy upon Nf is taken from this equation, that is sigma t is less than equal to Sy upon Nf, that is limit equation. We are going to combine these two limits in the primary design equation over here. Okay, and then we are going to get this one. Okay, we are going to get this one, that is C rho F NF L minimum divided by SY. Now what we are going to do, we are going to separate the term, that is a functional requirement parameter, material parameter, and geometrical parameters. Okay, now F upon MF NF functional requirement parameter, L minimum geometrical parameter, and C rho upon SY is the material parameter. So these are separated, these are the separated one. So this is the final PDE in order to minimize the cost of the material. Okay, now if you only separate, or if you think about this term, which C rho SY, okay, so based on this term the cost is going to be changed. Okay, because C maybe C rho SY is different for steel material, C rho SY is also different for cast iron, and C rho SY different for the aluminum. Okay, so based on this term we are going to choose the material, because how to minimize, that is the should be the minimized one. So accordingly we are going to select. Now similarly this is what discussed over here, selection of material. C rho SY calculated for all the available feasible material. Okay, feasible materials may be the steel, cast iron, aluminum, and so on, and the lowest value of C rho SY is selected. Okay, for example, for the steel I am going to get 100, for aluminum I am going to get 90, and for cast iron I am going to get the 70. Okay, so 70 is the lesser value, so I am going to select the cast iron. Okay, so in this way this is going to be work, that is optimization. Okay, now determination of elimination of the parameter. The eliminated parameter can be determined by the subsidiary design equation. Okay, that is SY upon NF is equal to F upon A. So that is what we are going to eliminate. How? That is A is equal to F into NF divided by SY. Okay, and the last, that is the determination of optimum quantity. Determination of optimum quantity. Okay, so finally the most significant undesirable effect can be the minimized, that is the CM is determined by the primary design equation. That is what the earlier we have done, that is CM is determined by the primary design equation, which is present over here. Okay, which is present over here. Okay, so that's it. Okay, thank you.